Dear colleagues, let us continue the last session of our workshop. The next speaker is Dr. Aristarkhov with a talk about Heisenberg's uncertainty principle and particle trajectories.
Hello, everyone. First, let's check the connection. So everybody hears me nicely. Yes?
Yes, we hear you and we
Right.
see you.
Great. So I'm glad it works. First of all, I want to thank the organizers for inviting me, and in particular, Vladimir Alexeyevich Petrov, who wrote to me and walked me through the whole registration process. I'm really happy to be part of this workshop. And also in the timetable, it's even written that I'm a professor. So I'm actually not even a doctor. So I'm finishing my PhD now. So my supervisor was Professor Dr. Detlef Dürr, who is on this photo. He passed away in 2021, in the very beginning. He was really a remarkable person, loved dearly by all his students as a father. And what's important now is that he also was a great scientist, and I recommend everyone to read his papers and to watch these videos with him. There is one interview and one talk of his on YouTube. And I dedicate this talk to him. So let's jump now to the essence. So this is a talk on Heisenberg uncertainty principle. And this is something that we learned during, I think we all learned during our first course in quantum mechanics, or maybe even early in school. And it was told to us definitely that it is a fundamental thing, which was groundbreaking, and this is part of the foundation of quantum mechanics, and definitely something of a tremendous fundamental significance. So what is this significance? Why was it so important? What is the message of the uncertainty principle? And I think it is nicely phrased by Max Born in his Nobel lecture. So I give you just a few moments to read this quote. Okay. So let me just put it in a nutshell. According to quantum theory, there are no point particles moving on trajectories. This is what Max Born was saying. And this view has made its way more or less everywhere, yes, in all the popular lectures, all the, I think that even some of you have taught that during your lectures that you have given in the universities. And many of our favorite textbooks, in particular this one that the large part of the audience knows very well, tells us the following. So it's the page 2 of Landau and Lifshitz, volume 3. Once again, I give you just a few moments to recall this quote. Yes. So this is the message of the uncertainty principle. And the message is there are no point particles following trajectories. And at the same time, we know that this message is wrong. So there exist empirically adequate trajectory containing quantum theories. And just in a few examples, well, it's not that there are very many of them, just more than one. So one of them is called Bohmian mechanics. And this is the theory that we worked a lot with in our group. And actually, this is not even a one theory, it's a kind of group of theories which are slightly different. And I know of at least one more, which is called Nelson's stochastic mechanics. I don't know, I'm not very familiar with this theory, but it's worth mentioning. All right, so I can imagine that the existence of trajectory containing quantum theories may come as a surprise to at least a part of the audience. And so I thought I am obliged to give a short introduction. So a very brief introduction to Bohmian mechanics, which is the most prominent example of such a theory. You may also know it or heard about it by the names of de Broglie-Bohm theory or pilot wave theory. It was discovered by de Broglie in 1927, presented at the Solvay conference, and rediscovered later by David Bohm in 1952. So what does the theory tells us is the following, that the world consists of point particles which have positions, and the particles do follow trajectories according to the guiding equation, which has the form that you see in the slide. It's just a first order differential equation for every particle. And the velocity field here, which is on the right-hand side, depends on psi, which is the solution of a wave equation. And now, depending on in which regime we work, let's say in the relativistic or non-relativistic, and depending on if we consider particles with spin or without, we take different wave equations, and this guiding equation also changes the form. So for example, for non-relativistic spin zero particles, it looks like this. So I just give you a few moments to have a look at this formula. So this, for example, this vector J is called quantum probability current or quantum flux. Sometimes it's, I think, known for most of you. All right, and the wave equation is simply the Schrödinger equation size, just complex valued for non-relativistic spin zero particles. So for I don't have time to discuss the other regimes, but I give you some references, and of course I'm also ready to share the slides after the presentation. So sometimes it is said, it's one of the charges that Bohmian mechanics often faces, that it cannot treat spin, which is totally wrong. So people who say that simply are not familiar with the theory, I didn't read it. Read the papers on it probably. So already David Bohm has offered how to treat spin in Bohmian mechanics, and nowadays this question is well researched, and also the singular relativistic particles can be treated, the Dirac particles, and the bosons too. So far so good, but I haven't told anything about the empirical adequacy of the theory, and I should. And first of all, let me say that Born's rule holds in Bohmian mechanics, and there are two ways of approaching physics, I would say, in a way that you get the Born's rule. So the first way is that you may treat subsystems, just apply Bohmian mechanics to subsystems as if they were the whole universe, just like we do using the standard formalism. So we assume that in certain situations, for some reasons, the subsystems of the universe of our interest behave as the rest doesn't exist, so they are completely isolated. And then if you assume the Born's rule at the beginning, t equals 0, then by virtue of the velocity field v, the Born's rule is going to hold for all times. So this happens because this velocity field v, which depends on the wave function psi, satisfies the continuity equation. There is another approach. You may start applying Bohmian mechanics to the whole universe, and then you may derive the Born's rule for subsystems using the techniques of, well, which are very similar to those of classical statistical mechanics. This result holds for the universe consisting of spin zero particles. So So the generalization with spin is not yet obtained. So this is maybe one of the exciting research projects in the theory. All right. Apart from that, Bohmian mechanics gives correct predictions for all known non-relativistic experiments like measurement of position we have just discussed, here's the Bond's rule, momentum, spin, scattering situations, and experiments with singular relativistic particles. So as of today, there is no Bohmian mechanics for the systems of many interacting relativistic particles. And this is, well, people trying to get it. And this is one of the open problems too. All right, so I just told you that the theory is empirically adequate and gives correct predictions for so many experiments. So I feel obliged to give at least one example. And this is maybe the most famous experiment in quantum mechanics, the double slit experiment. This is the experiment about which Feynman was saying, and also in Landau-Lifshitz, it's also written that it is absolutely impossible to reproduce the results of this experiment, assuming that the particles follow trajectories. This is not the case. So you may actually model the double slit situation and calculate the Bohmian trajectories, which will look like this. And you see that if you put the screen here on the right, and scintillations appear where the trajectories enter, what you're going to see is the familiar interference pattern. All right. Okay. So from now on, I will count this assertion as established. So there exists empirically adequate trajectory containing quantum theories, for example, Bohmian mechanics, which means that there has to be something wrong with the arguments of Heisenberg and the Copenhagen school, and we would like to find out what. So we start with the arguments of Heisenberg of 1927, presented in his famous paper. It is also the paper where the uncertainty relation appeared for the first time, and that time it had such a unfamiliar to us, the form unfamiliar to us. It's not how it appears today. But it seems that Heisenberg's argument of 1927 did not rely on the uncertainty relation. So what Heisenberg did instead was the following. In, I think, first paragraphs of the paper, he redefines the familiar notions of position, velocity, and trajectory in the following way. So I give you again just a few seconds to read the quote. All right. So what Heisenberg says is that whenever I say trajectory or velocity or position, I have to mean certain laboratory operation suited to measure the corresponding thing. Yes, so now these words are mere placeholders for the laboratory operations. Okay, so what Heisenberg says regarding measuring trajectories of the electron. So again, I give you a few moments to read the quote. All right, so notice that Heisenberg acknowledges that it is possible to measure the trajectory of the electron, at least in certain situations. And he also not says himself that it is not necessary to measure position and momentum of the electron simultaneously, but rather just to make consecutive measurements of positions. But he says that the difficulty of measurement of the trajectory in an atom is rather related with the fact that such a measurement would just, the first measurement of position would destroy the atom. All right. So, as I said, it doesn't seem that his argument relies on the uncertainty relation. So let us summarize the argument. Heisenberg says, whenever we are speaking of trajectory, we should mean the laboratory operation designed to measure trajectory. Since there is no such laboratory operation, then this word has no meaning. So we could go now into the deep waters of philosophical discussion of operationalists against non-operationalists. But I wouldn't like to do that. I would like just maybe a bit emotionally to point out the following. Well, this argument is clearly circular, at least to me, because the expression that Heisenberg uses, so the definition of the word trajectory, or some other word, so definition of some entity x definitely contains the x. And it is also very vivid in this quote, where Heisenberg explicitly determines what he means by the path of the electron, namely the consecutive places in space, positions in space that electron occupies. But then he says, but this word has no meaning. So he defines the word, and then he says, no, but it has no meaning. So this sounds very circular, at least to me. So I would like to move to the Heisenberg arguments of 1929. All right, so what I mean by that is the arguments which are presented in his famous Chicago lectures. And I have to say, these are pretty different from the ones presented in 1927 paper. This is, in the Chicago lectures, we find the uncertainty relation in the form that we know from the modern textbooks. Yes, the relation which involves standard deviations of position and momentum. And this relation is, of course, just a mathematical fact. And interestingly, it was proven not by Heisenberg, but by Kennard in the same year. And well, it's not that Heisenberg was not aware. So he was not like Einstein, not mentioning other authors, but he just explicitly quoted the paper by Kennard. And so the empirical input of this inequality, I think, is also clear to us. And this is the following, that if we have two ensembles of, well, two large ensembles of several similarly prepared systems, so such that initial wave function is the same for all of them, and let's take them one particle systems for simplicity. And then we make a position measurement on the first ensemble, and we get some distribution. And then we perform the measurement, which is called the momentum measurement, on the second ensemble, and we get some distribution of momentum. And then if we somehow quantify the width of these distributions, or just take the width of those distributions and multiply them, it turns out that whatever we do, the product of those width has to be larger than h bar, or h bar over 2, depending on how you exactly define the standard deviation. Yes? Okay, but so this is clear, but it seems to be a bit far from claiming that trajectories have to be bound from the theory. So let us find out how Heisenberg has made this connection. Again, so here's the now very important quote. So please read it. I'll give you a few seconds. All right. So what does Heisenberg say in this quote? He says that because of the uncertainty relation, the empirical verification of the existence of trajectories is impossible. So it is a matter of personal belief whether they exist or not. So let's break down this argument and first discuss what counts for Heisenberg as experimental verification. He is not explicit about that, but I think there is only one way to understand these words in such a way that his argument makes sense. And this is the following way. So let's say we find the position of a particle to be Q0 with accuracy epsilon Q. So we know that the particle is now in this region. Simultaneously, we also find experimentally whatever other initial data we need to calculate the future trajectory of the particle. And for Heisenberg, this initial data is clearly the momentum. Then we have a look how this region in space is going to evolve under the flow of the theory that we have in mind. Yes, so we simply propagate every point that we have here with the initial data that we also have, and we obtain some region of space which I called U tau, because tau is some later moment of time. Then we also require that the size of this region is again of the order epsilon Q. And then we make again a measurement of the position of the particle and find that it is somewhere in the region B tau. Now, if B tau and U tau cross, then we say that we have experimentally verified the existence of trajectory. And we say that only if this works no matter how small epsilon Q is. So if we manage to measure the initial position very accurately, then U tau also has to turn out small enough. And this has to be true, yeah, for every epsilon Q. All right. Okay, so now when we figured out what experimental verification means, we would like to know how it follows from the uncertainty relation that it is impossible to have this experimental verification for quantum particle. So let me notice that to do this, we first have to assume that there are trajectories, yes? So that quantum particles, so we have to assume that quantum particles do follow trajectories, and then we can show that such experimental verification is impossible. So Heisenberg doesn't explicitly assume that. Well, he doesn't state, of course, some law of motion or something like we did when we discussed Bohmian mechanics, yes? But he has definitely in mind certain law of motion. He definitely has in mind that trajectories do follow trajectories. And I have to say that the implied law of motion has a lot in common with Newton's law. So the initial data that Heisenberg uses, so for him, these are position and momentum. So apparently the law is second order. And also he clearly assumes that in the absence of interactions with other bodies, trajectories are straight lines. So also the first law of first Newton's law. And this is, yeah. So let's move on. Now the wave function, Heisenberg of course also has a wave function, and it clearly has epistemological character. So whenever he speaks of the wave function, he speaks of knowledge, of our knowledge about the particle. Then for him, it's not something which is subject to analysis. It just comes out from this definition of the wave function, that if we measure the position of the particle with a given accuracy, epsilon Q, then the width of the wave function right after the measurement, for example, measured by delta Q, has to be equal to this accuracy. So this is why I use here the sign of equivalence, because it's, once again, for Heisenberg, it's not subject to any analysis. He thinks, so he doesn't even comment on that. He just assumes that this is the case. For him, it's just evident that these are the same things. And this is because of the role of the wave function that he assumes. All right. So now, if we determined the position of the wave function or the position of the particle with a certain accuracy, now let's ask how accurate can we determine the momentum. So according to Heisenberg, we can determine the momentum of the particle prior to the position measurement, so which is called here P prior. And then if we know the disturbance introduced by the disturbance of momentum introduced by the position measurement, then of course we can find the momentum right after the position measurement. Yes. So our knowledge of the momentum right after the measurement is determined by the accuracy with which we can find out the disturbance of the momentum introduced by the position measurement. But at the same time, our knowledge of momentum is determined, according to Heisenberg, by the Fourier transform of the wave function, which has the width delta p. Therefore, for Heisenberg, delta p is equivalent to this epsilon delta p here. And finally, the uncertainty relation comes into play. So because of the epistemological character of the wave function, for Heisenberg, once again, these quantities epsilon q and epsilon p and delta q and delta p, these are just two pairs of equivalent quantities. This is why this equality works, and this is just a familiar uncertainty relation, which is a mathematical fact. All right, so let's recall now the picture of experimental verification that we had. Yes, here it is. So now for Heisenberg, of course, clearly, this epsilon q and epsilon p cannot be made arbitrarily small simultaneously, correct? So eventually, when you make epsilon q small enough, epsilon p is not going to be smaller, but even going to grow. But according to Heisenberg, right after this simultaneous measurement of position and momentum, the particles are going to follow straight lines, and the lines are parallel to the momentum vector. So if the accuracy with which we know the momentum is low, means that this region where they may end up, starting here, is very large, because that would be just the straight lines going outwards in all directions. So even if this region is small, the region where the particles may end up in is going to be very large. So this is how Heisenberg argues that from the uncertainty relation, it follows that we cannot experimentally verify the existence of trajectories. And according to him, this is enough reason to say that it is a matter of personal belief if there are there or not. Okay. I think, so this is a summary of Heisenberg's argument in 1929. And then we have just done it. So just skip this slide. So now a small lyrical digression. Just have a look how much time I have left. Okay, 10 minutes. I think I'll manage. Yeah, thanks. I think I'll manage. So when I first learned the uncertainty relation, yes, in this form, this one that we have discussed, which is a mathematical fact, I kind of also understood what its empirical input is, yes, with these two ensembles and the width of distributions. But at the same time, I also knew that Heisenberg used the gamma microscope experiment as an illustration. And let's just recall the gamma microscope thought experiment. There, Heisenberg says, we shine light on the electron and we determine its position. And simultaneously, from the scattering angles of the photons using the theory of Compton effect, we can find out what's the momentum of the electron after the after this measurement is, after the position measurement. So clearly, he discusses simultaneous measurement. So not the repetitive measurements, is one ensemble and their only position, and another ensemble and their only momentum. But then, but the simultaneous measurements. So in one run, we try to find out both, and I couldn't figure out how does this come together. So both things come from Heisenberg, actually from the same work. Gamma microscope thought experiment also appears also in 1927 paper in 1929. And for a long time, I couldn't figure out how this comes together. But now it's clear. So in the gamma microscope thought experiment, which Heisenberg in Chicago lectures calls the illustration of the uncertainty relation, so of this relation here, Heisenberg clearly discusses the quantities epsilon q and epsilon delta p, meaning the accuracy of the position measurement that you can achieve with a gamma microscope, and the accuracy of the momentum measurement, of the disturbance of momentum introduced by the position measurement. And he used some analysis. He used optics and the theory of Compton effect and the theory of microscopes, and he finds out this relation. But for him, it is nothing. It's not surprising, and it's mere illustration of what for him is evident. That of course every of those quantities is actually equal to delta Q and delta P, and he already knows, and as he himself says, that Kenneth has showed that these two quantities, the product of them has to be larger than h bar. So yes, that's why he calls it illustration. All right, so now we have understood what the argument of Heisenberg in 1929 was. So let's ask the question if the analysis was correct. And I would say the answer is definitely no, for the following reason. So the implicit trajectory containing quantum theory that Heisenberg used postulates that the probability density of the velocity, and here it's important that here the probability density, not of the results of the experiment, like people usually measure momentum, yes, in some asymptotic regime. So it's not what is meant. But the probability density of velocity as a tangent vector to the trajectory of a particle with a wave function psi is given by the Fourier transform psi. But you can check using some simple examples that such velocity field would in general fail to satisfy the continuity equation. So remember when I was discussing the Bohmian mechanics and why it is empirically adequate, I was saying that it is important that the velocity field satisfies continuity equation in order for the Born's rule, in order for the theory to be compatible with the Born's rule. So such velocity field that Heisenberg assumed is not going to be compatible with the Born's rule. Okay, so the analysis is false, or I would say it's irrelevant, because the theory which underlies it just doesn't have anything to do with our world. But is it true that in any empirically adequate trajectory containing quantum theory, Heisenberg empirical verification, as we have discussed it, is impossible? First, I want to point out that in order to answer this question, the analysis in a generic empirically adequate trajectory containing quantum theory is required. But such analysis is absent. What we have is, so in Bohmian mechanics, we can do such analysis, and the answer is yes. So although Heisenberg's own analysis was incorrect or irrelevant, but the conclusion is correct, at least for Bohmian mechanics. So unfortunately, I don't have time to justify this conclusion, but I give some details in the paper on which this talk is based. So yes, so empirical verification, in a way we have discussed it, is indeed impossible, at least in Bohmian mechanics. So we naturally come to the following question. Let's say we have a trajectory containing quantum theory or a good old psi-complete theory. Is it a matter of personal belief which one to choose or not? So the answer depends, of course, strongly on what we require from a physical theory. So let's require that physical theory is just a set of rules allowing us to obtain numerical predictions for experiments. Then, as we have already seen, trajectories in quantum theory or trajectory in quantum world do not allow us to give accurate predictions for a particle's position. At the same time, the calculation of trajectories requires the solution of an additional equation. So why bother? So it seems that the wave function is well enough. This is indeed the case unless we notice that there is actually a big class of experiments for which standard quantum formulas does not give predictions. And this class is time of arrival measurements. And I would describe this class as follows. There is a particle or several particles or many particles, which is confined first in a certain region of space and then released at the known time, which is set to 0. Then a detector of given geometry is placed at a certain distance from the region of initial confinement. And of course, at some time tau, the detector is going to click. This experiment is repeated many times. We'll probably have always different results. So these times tau are not going to be the same every time. And we are going to have a distribution of arrival times. And the task is to predict it. So first, how do we usually solve this problem in the quantum formalism? Yes, we use the operator, the self-adjoint operator, but it was noticed already by Pauli that there is no canonical time operator. And the book is of 1980, but I think the theorem is from 1930s, so long ago. So this result gave rise to a plethora of different add-ons to standard formalism, all aiming to produce arrival time statistics, and of course, at best in a very general case. And many odd add-ons have been suggested, but the adequacy of many of them is questionable, and the range of applicability of them is also limited. And here I would need many references. That's why. So I again, so the references are given in the paper. So please have a look. It's now on archive, but it's going to be published in Springer Foundations of Physics soon. Yes. And at the same time, in trajectory containing quantum theory, in particular in Bohmian mechanics, the prediction of the arrival time distribution is a problem with almost obvious solution. If particles follow trajectories, the time when a given trajectory crosses a certain surface can be easily calculated, and the arrival time distribution can thus be obtained if the distribution of the initial positions is known. So if for a very particular experimental setup, which is even realizable by today's technology, you can have a look at this reference. And it's a paper by my colleague Sudhan Das and by our supervisor Detlef Dürr. There they have also very intriguing results. All right. So if a physical theory is a set of rules allowing us to obtain numerical prediction, so if this is what we require from the physical theory, then as I have just argued, trajectory containing quantum theory is preferable. But we actually can ask for more. So we can ask of a physical theory to tell us what the world consists of, how the constituents behave and how it results into our observation. So the theory has to state what there actually is. One says the theory, in this case, has a clear ontology. The theory has to furnish a dynamical equation describing the behavior of what there is, so the constituents. And trajectory containing quantum theories, in particular Bohmian mechanics, are clearly like that, and psi-complete theories are not. So if we want this from a physical theory, we clearly would prefer the former over the later. Okay. So there are some concluding remarks, and instead of reading them out and spending time, I just would leave them here so everyone can read. Thank you very much for your attention, and I'm ready for the questions.
Thank you, Sergey. So questions, comments, I see Vladimir.
Thank you very much. Thank you, Sergey, for your lecture. Maybe I didn't catch the essence of what you have told, but if I take, for example, the Ehrenfest equations for the average distance and for the average velocity, and I can consider this as an average equation according to which I can, in principle, calculate so-called average trajectory, isn't it?
Okay, let me think. First of all, isn't this going to be Newtonian, no? I mean,
yes, you just take, and it doesn't matter, but it is Newtonian, yes, if you take the Hamiltonian Newtonian. So the Ehrenfest equation is just the repeating of Newtonian equations in average. And in average, in this sense, we can argue about average trajectories.
You may do the following. You may of course say, well, you are trying to construct theory, yes, where the particles follow trajectories.
Yeah.
And you could have a law which is different from what, for example, from the one of Bohmian mechanics, and which is somehow based on the Ehrenfest theory, Ehrenfest equations.
Yeah.
But I'm afraid that this theory is not going to reproduce the Bond's law. So of course you will have some theory where the particles follow. Well, I think the trajectories are even going to be Newtonian, aren't they? Because Ehrenfest equations, but then it definitely, for example, such a theory wouldn't reproduce the double slit, wouldn't it?
Yes, theoretically we can calculate this average trajectory, but then certainly I will ask in which way I can check this with measurements. This is a problem which I don't know how to answer.
Could you repeat the last questions?
You can calculate certainly from the Ehrenfest equation the quantity which you can consider as an average trajectory. You can do that in Newtonian physics with simple Hamiltonian, for example. But then having in hand this t-dependent function, so it remains to argue in which way we can follow this trajectory. And certainly here maybe I have found myself the negative answer to my proposal. Okay, thank you.
Okay, all right. That is good. Yeah. Thank you for the question. Some other questions?
Okay, one more question, Georgi.
Sorry, yeah. I did not catch, is there any experiment which distinguishes between these two theories, what we call the regular quantum mechanics and this one? I mean, are there experiments where prediction of quantum mechanics says one result and this trajectory based says that another? Can we differ them by an experiment?
The relationship between those two, let's say we have a standard quantum mechanics, a standard quantum formalism, and we have Bohmian mechanics. And so here, as I wrote in the last sentence, so the set of experiments for which, let's replace now for simplicity, trajectory containing quantum theory, just Bohmian mechanics gives unambiguous predictions is strictly larger than that of psi-complete theories, strictly larger than, for example, of standard quantum formalism. It means that it's not that there is some experiment for which both theories give predictions and you may distinguish. It's just that there are experiments, namely time of arrival experiments, for which the standard formalism simply doesn't give predictions.
And what do you mean doesn't mean prediction? No prediction at all?
Like you may try and you will, you know, it's in general, it's a recipe, yes? I would just recommend to try. Imagine that you may even start with a, I don't know, one-dimensional example or something.
So
You just have one particle which is confined. Let's say we have one particle on a line, and it's initially confined between 0 and 1, and there is an infinite potential barrier there, and then you release it, and you ask when is it going to arrive at the point 5, for example. How would you approach this problem?
I don't know. I just wanted to find out, is there at least one experiment really measurable in the real life where these two theories give the different results and we can compare and say which one is right, which one is wrong relative to this experiment?
The short answer is yes, and not even one, but many. And but the thing is, once again, it's not that two theories give different predictions, or maybe they do, just like the empty set is different from the set which contains something, you know? So one theory simply doesn't give, it's not applicable. When you try, you just can try to, you know how people usually do it, yes? There is an experimental setup, you can model it, and you can get the predictions. And you can try to do it using standard formalism, get predictions for a time of arrival experiment. You will simply fail, so you won't be able to do that.
Okay, thanks.
Okay, no more questions. Sergey, thank you once